So our experiment is on the effect of pH on dye-sensitized solar cell efficiency. And I'm Owen.
I'm Tianjun.
I'm Daniel.
I'm Isha.
And I'm also Isha.
All right, so since the energy crisis is occurring, the amounts of fossil fuels in the world is steadily decreasing. So we need many forms of alternative energy, one of which is solar cells. Currently, silicon solar cells are used as a main device to get approximately about 25% of the light from sun and convert it into energy. The silicon solar cells are very expensive, however, and most people cannot afford them. So, as an alternative, dye-sensitized solar cells were created, which are cheaper and less efficient solar cells. These solar cells are made of natural dyes, including beet juice, and they are cheap, environmentally friendly, and biodegradable. So the significance of solar cells is that currently silicon solar cells are way too expensive for many people to afford. So if we were to make dye-sensitized solar cells more efficient, more people would be able to use them and change from the fossil fuels onto solar cells, which would greatly decrease the greenhouse gas emissions and save fossil fuels.
So the question that we researched was how do varying levels of pH in the anthocyanin dye of a solar cell affect the amount of current generated? So we researched pH because most of the other aspects of like the solar cells, like the wavelength of the dye or like the color of the dye, that was already like widely known. So like we decided to test the pH of the dye. And so we hypothesized that if we decrease the pH in the dyes of the solar cell, the current produced will increase because lower levels of pH create more ions, which have more excited electrons, and like the more electrons there are, the more energy that they will absorb and produce. So, yeah.
Okay, so to help you guys better understand our experiment, I sort of put together a diagram, and you can see that we need two conductive glass slides, and the conductive side, because there's only one conductive side, of the glass slides are both in between the other materials, and then we coat carbon, which is in the form of graphite from pencils, onto one of the conductive sides, and then we coat the chemical TiO2, which is already said in all the previous experiments pretty much, on the other conductive slide, and we add a layer of iodine and the beet juice dye that we're using. So normally when a light source comes in, it usually comes from the top. So a electron from the light source, it will come in from the top. It will be attracted by the beet juice dye, and it will be excited so that it can jump onto the conductive slide, and then through the help of an outside source, which in this case we used a clamp, it will travel all the way around and then end up on the top side pretty much, and then it will go back downwards again, but this time it will go into iodine, and it will cause a redox reaction, an oxidation reduction reaction, which will allow the electron to flow through the iodine, and the carbon essentially acts as a catalyst, or this redox reaction would never happen, or it would happen, but it would take very slow and it wouldn't be efficient, and so that's how we get the electric current flowing. And right now, if we add another external source to the side, it will pretty much be powered by the flow of electrons. And this is how we put together our solar cell. Is to give you guys a better understanding. This is how we put it together, with the dye on one slide and the carbon on the other side, and then we put together like this with like a little edge on the ends to clamp, so we can clamp the electrical current multimeter onto the sides to allow electron flow. And then here's the clips. Here's the clips I talked about with the iodide solution in between the cracks. So we will drip it in there and then wait till it seeps through, so we will get an even layer. And after we assembled the solar cell, which looks like this, we will measure the current with the multimeter, which is right here. And I don't think you can see in this picture, but the red and the black wires will have little clamps that we will clamp onto here and here. And then we will shine a light through it, which is either the flashlight or the projector. Those are the light sources that we used in our experiment. And we will repeat this process. We use a different range of pH, 4.7 to 6.7 in 0.5 intervals. And then we make the different pH dyes by adding acid or base, these two, acid or base, 1 molar HCl or 1 molar NaOH. And then we keep track of the pH by using this pH meter, which is this, and this machine in the background. And one thing I should mention is that we use beet juice just because, or not just because it has anthocyanin, which is what we want to use in the dye, but also because it doesn't change color drastically under this range of pH change. So maybe it will change color on the bigger pH change, but then not on the ones that we're testing.
Like Robert said, we collected data using 2 light sources, and one was the projector and the other was a flashlight. So the reason we didn't use sunlight was because since this is just preliminary research and we only had 2 days to do it, in like a perfect situation, we would test it over a long period of time in sunlight, so we would get a better reading of current, and small factors like clouds wouldn't greatly affect our data, whereas if we did it over 2 days, our data would be skewed. And so when we tested the pH of the beet juice, it was 6.2. So this kind of acted as our control. And we went up in increments of 5 so our research showed when we researched online, we found that lower pHs are often associated with better current and so better efficiency. So we decided to conduct in increments of 0.5, 3 times below. So we did 4.7, 5.2, 5.7. So we tested more acidic levels rather than basic levels since we only tested 1 basic. And what we found was that there tended to be a more optimal pH, and this happened around the pH of 6.2. As you can see in the graph, at 6.2, our graph seems to have a higher current produced. So in our first trial, our very first trial, you can see we kind of have an outlier at 6.2. This was because it was the very first solar cell we made, and we weren't as used to making it, and there were some errors that happened. But when we did it for the second and third trial, we found that results greatly increased, and this is because 6.2 was the optimal pH. And on this graph, this tested the flashlight. And you can see here again, 6.2 is the optimal pH, and it gave a current of 4.1 microamps and 3.2 microamps. And so what we concluded was the optimal pH was indeed 6.2 for the best efficiency. And you can also see in the graphs that at 2 acidic levels, the current produced is super low, and at too high of a pH, the current produced is also low. So we found that if the pH is too high, that it was due to a chemical deformation in the structure of the anthocyanin dye, and it was more specifically in the flavillum cations in the anthocyanin dye. So anthocyanin is the colored part of the beet juice. And because there were a lack of flavillum cations, which is the part of anthocyanin that absorbs light, if there's less of these cations, it will absorb less light. And because there's less absorption of light, there's less current produced, therefore it's less efficient. And with the lower pH, we found that too low and too acidic of a pH, it starts to degrade the properties of the dye. And so what we found is that after the maximum efficiency pH, acid starts to lower solar cell efficiency.
Okay, so we conducted this experiment because it can be applied at a much larger scale, such as in fuel and energy to power your cars, such as a Tesla, because we're Team Muskie. Shout out to Elon Musk. And it can also be used to power your small devices, such as your phones, calculators, computers, and batteries. And the dye-sensitized solar cells can also be applied to windows on the side of buildings. And it was, when we looked up on our research, we found that in a past experiment, to keep it real brief, it was found that a circuit module was modified with dye-sensitized solar cells, and that the module with the parallel circuit generated voltage that tended to be constant, which resulted in small efficiency compared to the module with a series circuit. So the series circuit had a higher efficiency, which shows that this is a much cheaper alternative to the silicon solar cells, which are really expensive today. And so in our further experimentations, since we only had 2 days and we could only test only pH, because we could have tested higher pHs, because like Robert said, lower pHs don't change the color of the beet juice when in the specific pH range that we tested. And we could also test it in a different light source, such as sunlight, because we only used the projector and the flashlight. And sunlight is more relatable because it's a daily life thing that we all are exposed to, and it could be more useful information for the future. And we could also test different catalysts. So we use graphite as our catalyst in the solar cell. So we could use something like nickel or chromium, which they're transition metals. So they easily lend and take electrons from other molecules. And just to be brief, a catalyst is a chemical substance that increases the rate of a reaction but doesn't change the thermodynamics of it. And if we wanted to, we could also test for different colors, which have different wavelengths, since we only tested pH. And we could have also used a different dye. So instead of using something like beet juice or raspberry juice, we could have used cabbage juice, because it changes color drastically based on pH level. So if we wanted to test color, that would have been a good alternative. And finally, we could have done different tests for smaller ranges of pH. So we use increments of 0.5 from 4.7 to 6.2. So we could have done something on a much smaller scale from like 6.15 to 6.25. Okay, thank you for listening. Any questions?
Nice experiment. One quick question about your projector, that chart. There's only one pH that pushed the. So how are you sure those two are not outliers?
Do you mean the two with the numbers?
pH 6.2. I know the other chart is more showing you the trending is going up, up, up. And this one is like staying low for the projector, and all of a sudden there's one jump. I figure it might be better if you add 2 more data points, left and right, to show the trend, to confirm it's not an outlier going up instead of going down at 6.2.
Yes, because that would be one of our further experiments. So one of our further experiment is testing whether higher or lower pH, and I agree with what you were saying, because you can add like another data point on both sides and make the pH range a little bit bigger, and we just chose this range because it's easier for us to like control it. because like initially we wanted to like calculate how much we needed, but that's like pretty much impossible. So we just like decided to drop, which is like way easier and more efficient. But like that means we kind of had to like limit our pH range. But if we have more time and if we had access to like better, or not better, but like we have access to more equipments, we can probably test, probably even more than one data points on both sides, and that would be really helpful for our data.
So if the 6.2 pH was the optimal range or the optimal pH, do you have any like scientific reasoning behind why you think that is the case?
Well, it's not so much as reasoning, more than like educated guess. But we were researching, and then like we didn't think of much of like the acid and the base, and and the results sheet also shows why we think so. But then another like reasoning could be that maybe the acid or the base like it altered chemical structures like inside the cell, which could be an issue. And
So there's different theories that they have online too. So they found similar results, and the problem is, it's just the main part is the middle part is usually the optimal pH, and if it gets too acidic or too basic, that poses kind of a problem. And this data specifically applies to just simply beet juice, because it has a different amount of anthocyanin. The ones online did like raspberry juice or different juices that have anthocyanin, but a different concentration of it. So our theory is backed up by research, of course, but it's specific to beet juice. Yeah.
Thank you.
So I know you had it as a future thing to look at, but I'm curious about the possible lifespan of cells that you could make from this, since it is plant-based and could degrade fairly quickly. So what's your thoughts initially, without having done the experiment, on the durability and need to refresh this? And again, thinking about real-world applications, like if you were trying to coat, you mentioned windows on buildings or something like that. How often do you think that you would have to refresh it, or what would you do to increase the lifespan of it?
Wait, so do you mean like an initial consideration when it's compared to like other solar cells, or it's just like?
Well, just because, do you have any thoughts about what the lifespan of some of these might be because it's plant-based? And then what do you think you could do to extend the lifespan of it?
So this experiment was kind of to add on to that point. We were trying to increase the efficiency of our solar cell. And so there's many different aspects you can change to increase our efficiency. We simply just altered the pH of the dye, just the dye specifically. But you can alter every single aspect that we had in the other diagram. Like the TiO2, you could possibly use something else. And so the main thing about these solar cells is that they're cheap. So even if you have to refresh it, it would be very cheap. So, yeah.
So when you made so can you go back to your data where you have your the one with the highest current? So for solar cells, two things that affect how much current can be generated. One is area and the other one is intensity. Mm-hmm. So how do we know that highest current that you got there wasn't because you maybe made a bigger solar cell, slightly bigger, and maybe you didn't control the amount of intensity of light on the solar cell? Like, how do we know it wasn't one of those geometric factors versus actually what you're claiming, which is the pH?
So for each of our trials, we use the same amount of like electrode glass with the same surface area. So that was constant. And also for the projector and the flashlight, we always put the electrode glass right, like we put it pretty much on the flashlight or projector.